Hello, I'm Patty Simpson with Simpson Math. In this video, we're going to use the formula for the hypergeometric distribution to solve probabilities. In a previous video, we looked at what made a hypergeometric distribution hypergeometric. And we saw that we needed a population of items that we were choosing a sample from, choosing a few from, without replacement. We're going to use a capital N to denote our population size and a lowercase n to denote our sample size. We've done that in the past in statistics. We use a capital N to represent how many are in our entire population, in our entire group. And the lowercase n we use to denote how many we're choosing from that, how many of those we're choosing out. We're going to do the same here. Here, our K is the total number of successes. So in that previous video, we saw that we could divide our objects into two groups, successes and failures. And the total number of successes we're going to denote with a lowercase k. And then from those total number of successes, we're going to be looking for some of those to be chosen, which will be our random variable of x. And then the formula, well, with probability, our total number is always on the bottom or in the denominator. And here we have the total number of ways that our sample can be chosen from our population. And this is the combinatorics formula, or the combination formula, and we'll look at that here in a second. And then on top, this is the number of ways that we can choose our successes, the number of successes we're going to choose from our total number of successes. And we're multiplying that times, well, when we do the population minus our total number of successes, that's going to give us our total number of failures. And from that, we're going to choose a certain number of those failures. So that'll be on bottom. These guys, this bottom and this bottom, should always add up to be our sample size. And this number plus that number should always add up to be our population size. So let's take a look at how this formula will work. First thing we need to do is recognize what are those numbers. So let's look first to find our population size, our sample size, our total number of successes, and the number of successes we're going to choose. So the total population here, we have a whole group of balls. So it says, given an urn with 8 balls, 5 green and 3 white, 4 prisoners must draw from the urn without replacement. The guards execute the prisoners who draw a green ball. What's the probability? Only 1 prisoner is executed. So we have a whole population of balls, and there are a total of 8 of them. That is our population size. From those, we are only going to choose, well, it tells me that I'm going to have to draw from the urn 4 of those balls. Each prisoner is going to draw a ball. So 4 are going to be chosen from the urn. Then my K is the total number of successes. So here I have to decide what is my success and what is my failure. I'm looking for 1 prisoner to be executed. So my execution there is going to be my success. That's what I'm looking for. I know it seems a little morbid, but that's how sometimes it works. Our successes sometimes are kind of morbid there. So that's just what we're looking for. And in order to be executed, they have to draw a green ball. So I'm looking to see how many total green balls there are in my population. And there are a total of 5 green balls. So my K in this one is 5. Then how many of those green balls do I want? Well, I want only 1 prisoner to be executed. So I'm only looking for 1 of those green balls. Now I'm just going to fill into my formula so that I'm looking for the probability that 1 prisoner is executed. Maybe you've seen it like this before, where your x equals 1. Then on the bottom of my probability is always the total number of ways. So we're going to look for how many ways can I pull 4 balls from the 8. Then in my numerator, I'm looking for the number of ways that I can get 1 green ball from my 5 balls. So Here I have 5 balls and I'm choosing one of them. But I was choosing 4 balls. So that means that also on top, I'm going to have some failures that I'm choosing. Well, how many total failures are there? Well, there are 3 of my failures, 3 of those white balls. And then in order for me to get only 1 green ball, that means the rest of mine have to be white, or I can subtract 4 minus the 1 to get 3 of them to be white. So if one prisoner draws a green, that means the other 4 have to draw the white. So, so now I'm just going to do my combinatorics, or my combination there. I'm going to plug that in. Remember, that's 5 factorial over 1 factorial times 5 minus 1 factorial. Here, this is 3 factorial over 3 minus 3 factorial over 3 factorial. On bottom, I'm going to have 8 factorial over 4 factorial over 8 minus 4 factorial. Now, when we do this work, we're going to end up with just 5 on top. Anytime we're choosing 1, we just end up with that top number. When the 2 numbers are the same, we always just end up with 1. Or you can do the work out here to find out that that's just going to be a 1. On bottom, though, it's a little more complicated, so that I'm going to do this subtraction to get 4 factorial. And then this 4 factorial, I'm going to write out as 4 times 3 times 2 times 1. Then my 8 factorial, I'm going to count down until I get to that 4 factorial. So I've got 8 times 7 times 6 times 5 times 4 factorial. My 4 factorials cancel. I'm going to do a little bit more simplification down here on bottom. Notice that 3 times 2 gives me 6. So I'm going to notice that this 6 divided by that 6 equals 1. Then this 8 divided by that 4 gives me a 2. This 8 divided by that 4 gives me a 2. Every time it should work out this way so that I don't have anything in this bottom denominator. I should be able to simplify until there's nothing left down there. So on top I have 5, and in the denominator right now I have 2 times 7 times 5. 2 times 7 times 5. I'm going to continue to simplify before I multiply, so that notice this 5 divided by that 5 becomes 1. And then I'm just left with 1 on top and 14 on bottom. So the probability that only 1 prisoner is executed is 1 out of every 14 times that 4 prisoners draw the balls from the urn. So that's how we use the hypergeometric distribution formula. I'm going to do another example in the next video. Math Made Simple at Simpson Math. Thanks for watching.